In this question, we're again trying to figure out the differential rate law for a reaction. This time we're provided with graphs of initial rate on the y-axis against the initial concentration of each reactant on the x-axis. So it's important for us to start by knowing what the graphs look like for different orders of reaction. So for a 0th order reaction first, we know that the initial concentration does not affect the rate. So the rate is going to be constant regardless of the initial concentration. So as a result, we get a straight horizontal line on our graph showing the rate is constant regardless of what the initial concentration is. If we have a first order reaction, that means that if my initial concentration doubles, my rate also doubles. So my rate is directly proportional to my initial concentration. So that's going to have a graph shape like this. It's a straight line because that shows that if my initial concentration doubles, my rate also doubles. For a second order reaction, on this one, if my initial concentration doubles, my rate is going to quadruple. It's squared. So we're going to get a quadratic shaped graph like this. Finally, for third order, if my initial concentration doubles, my rate is going to multiply by 8 because it's doubled cubed, 2 to the power of 3, which is 8. So this one is also curved, but it's a cubic shape, which has a more dramatic shape. So it has a really steep curve like this. So those are the shapes I'm looking for my rate against initial concentration graphs to tell me what order my reaction is with respect to those things. So in this question, we have a fictional reaction between L2GR3 and E4. So we can see in our equation, we've got 2 L2GR3 plus E4. And our scientist conducts multiple trials with different initial concentrations of each reactant and measures the initial reactant rate. That's how they get those graphs provided of initial rate against initial concentration of each thing. So first looking at our order of reaction with respect to L2GR3. That's this graph here. We can see it's a curve. It's a gentle curve. It's not super dramatic. So that's a quadratic curve. That's our second order graph down here. So L2GR3 is going to be second order. For E4, if we look at the shape of our graph, it's a straight horizontal line. That is 0th order down here. And remember, that means our rate is not affected by the initial concentration. Our rate's just constant. So that's going to be 0th order. So now we've used the graphs to find our order of reaction with respect to the concentrations of each of our reactants. All we need to do now is figure out the overall order by adding up those orders for each of the reactants. So that's just going to be 2 plus 0, which is 2. So our overall order is 2. And finally, figuring out our differential rate law, same as always. Our rate is equal to K, which is a constant. Multiply the concentration of our first reactant, which is L2GR3, to the power of its order, which is 2. Multiplied by the concentration of our other reactant, which is E4, to the power of its order, which is 0. And remember, anything to the power of 0 just cancels to give 1. So we can cancel out that, and we're left with our differential rate law equation, which is just the concentration of L2GR3 squared. So we can find that here. There's our answer for this question. So you can see it works exactly the same as the other questions we've done, but we're now using graphs to figure out the order of reaction for each reactant. Let's do one more. In this question, we again have a fictional reaction, this time between R and MT3. So we can see in our reaction, we've got 2R plus 2MT3. This time we're given the differential rate law for this reaction, which is K, concentration of R, concentration of MT3 cubed. So let's go ahead and figure out our order of reaction for each thing. So for R, in our differential rate law, we have the concentration of R with no exponent, or in other words, it's to the power of 1. So that tells us the order of reaction for R is just 1. For MT3, that's to the power of 3 in our differential rate law. So our order of reaction is 3 with respect to the concentration of MT3. So we've got our orders of reaction for each component. To find the overall order, we're just going to add those up. It's going to be 1 plus 3, which is 4. So overall, we have a 4th order reaction. Okay, so we're then told the scientist conducts multiple trials with different initial concentrations and measures the initial reaction rate. They're going to get a graph of rate of reaction with respect to the initial concentration for both R and MT3. We have to guess what those graphs are going to look like. So let's start with just R. R has an order of reaction of 1. So looking at the bottom, for a first order reaction, we know the shape is going to be that straight sloping line because it's directly proportional. When the initial concentration doubles, the rate also doubles. So looking at our options, that's going to be graph 4. So the graph is going to be graph 4 for R. For MT3, that one has an order of reaction of 3. So looking at our options at the bottom, third order, that has that curve that's a kind of steep, dramatic curve because it's a cubic curve rather than a quadratic curve. So looking at our options, that's going to be graph 6. It has that steep, kind of dramatic curve, which shows our cubic curve for third order. So it's going to be graph 6. So as you can see, these questions are very similar to the previous skills. We're using our differential rate law. However, this time, when we got our order of reaction, we're linking that to the graph of initial reaction rate against initial concentration.